Hello and welcome to another video on probability. This time we're looking at events involving not and or, and we'll also take a look at odds. So in this video we're going to find the probability that an event will not occur, or we'll also look at the probability of one event or a second event occurring, one or the other. And then we'll use probability to help us understand and use odds and the difference between probability and odds. Alright, in the last section of notes, we looked at the probability of an event occurring, and we found it with the theoretical approach and the empirical approach. In this section, we're going to start off by looking at what we call the complement of an event, which is the probability the event will not occur. So if we know the probability of an event occurring, the probability that the event will not occur is simply just 1 minus that probability. Alright. The complement of an event E is every single possible outcome that does not satisfy E. So if we go back to our rolling of a die experiment that we kept talking about in the first section of notes, the sample space was 1, 2, 3, 4, 5, and 6. And we looked at one event being the probability that we roll 3. So in that case, 3 was the event, that was our E. Well, the complement of E would be everything else, would be the 1, the 2, 4, 5, and 6. So there's only one thing that satisfies E, the event. There are 5 things that satisfy the complement of E. Alright, and then the probability of not E and the probability of E, you can kind of take this equation or this one and you can rearrange them, and you'll have the probability of E plus the probability of not E is equal to 1. It's just doing a little bit of algebra. And that should make sense because one of the things we said in the last section is if you sum up all the possible outcomes, then you get 1. Well, E, which is the yellow one, and the blue, not E, all add up to every possible outcome. So it adds up to 1. Alright, so we get these rules from that if we know the probability of this thing, 1 out of 6, and the probability of that not happening is 5 out of 6. Alright, so that's how that's working. This notation down here, let me kind of fix it so you can read it a little better. So in set theory, we use this little bar, this little dash up at the top to represent complement. So instead of saying not E, we could also just say E complement. Oops, E with that little slash above it, E complement. That's the same thing as not E every time we see that. So you can replace that notation with not E, or you can just write the phrase not E. Either way, it doesn't matter to me, however you want to do it. Alright, let's look at an example. You're dealt one card from a 52 card deck. Find the probability that you're not dealt a queen. The card you're dealt is not a queen. Alright, well, the probability that I do get a queen, where does this 1/13 come from? So the probability of a queen, that's actually the same thing as the probability of a king. How many queens are there? There's 4. Remember our standard deck of cards? So this is asking about the probability of a queen. There's 1, 2, 3, 4 queens. There's always 4 of any one. We call these ranks. There's always 4 of any rank. So there's 4 queens divided by 52 regular cards, and then they both have a 4 in common. If you have a scientific calculator that will reduce, you can just type that in, 4 out of 52 math 1 into fraction for these TIs, and it'll reduce the fraction for you. But 52 has a common factor of 4. So the 4 cancels, the 52 cancels, and you're left with a 1 out of 13. So that's where this is coming from, this 1/13. And then we get a common denominator, 13/13, so we end up with 12/13. Alright, or what else could I do? Well, I could look at this picture. There were 1, 2, 3, 4 that were queens. Or I could just count it up. There's 1, 2, 3, 4, 5, 6, 7, 8. There's 4 each time. So 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, and then skip queens, 48 out of 52 that are not queens. You could just literally count them from here because we're just counting things that are not queens. That's what it means to satisfy the event. So there's 48 things. You could just say 48 out of 52. And then likewise, if you divide both by 4, you end up with 12 out of 13. So either way works. Count them or use the complement rule. These little rules that they give us, these complement rules and some of the OR rule that are going to give us in a little bit, what we'll see is as these things on the other side are typically easier to count or calculate than the thing that's isolated in these rules. But it's always up to you. A lot of times you have more than one option. You can do whichever one works best for you. Alright, now turning our attention to OR probabilities. Alright, every single probability we're going to use this rule for down here is going to have the word OR in it. Okay, in set notation, this symbol right here is called the union. And instead of reading A union B, which you can, we typically read it A or B, and that's why it's used in this situation. It's basically replaces the OR word, the union symbol does, when we're talking set notation, but everything else stays the same. Alright, mutually exclusive, that means that it's impossible for these two things to happen at the same time. Like if you're rolling a die, it's impossible to roll a 3 and a 4 because it can't end up on two sides at once. Right? Only one side can face up. So it's impossible to get both of these outcomes. So these are mutually exclusive events when you're talking about the rolling of a die. Alright, so that's what I mean by mutually exclusive, that no outcomes could possibly be shared. Alright, so let's look at this example with our cards again. What's the probability I draw a king or a queen? So there's the word OR, and that's what you're going to be looking for when you do these problems in your homework and on your quiz. If it has that word OR, then I can use this rule. Okay. Now we are going to get a second OR rule later for when they're not mutually exclusive, when they do share an outcome in common. All right. Now you may be thinking, well, what does it mean if they share an outcome? These, I can't think of one. Well, think if this said king or spade instead of queen. All right, there are 4 kings, there are 13 spades, but there's also a king of spades. So that's what we mean by they do share an outcome in common. Okay, but in this particular probability, or this particular problem, kings and queens, there are no outcomes shared. There's either a king or you're a queen. You can't be both. So we just add up the individual probabilities, and we've seen both of them. We've seen 4 out of 52 for king, 4 out of 52 for queen. That's 8 out of 52, which adds to 2/13. Or we've seen that these both reduce to 1 out of 13, and we could just do 1 out of 13 plus 1 out of 13 is 2 out of 13. Okay, this is using common knowledge, meaning that we've already seen the probability of king and queen reduced, and this is not. This is just saying theoretically there's 4 kings, there's 4 queens, they're both common denominators 52, so we add the 4's together and get a 52, or 8 over 52. So either way it reduces to 2 out of 13. Alright, well, what if they're not mutually exclusive? What if they do share common outcomes? Alright, if they're not mutually exclusive, then we're going to have this extra piece onto it. Alright, if you go back and look at the rule for when they were mutually exclusive, you just add probability of A plus the probability of B. And this is saying if they're not mutually exclusive, you still add the probability of A and probability of B, but because of the fact that they have outcomes in common, they've been overcounted. So you've got to subtract off the overcount. So that's what this is doing. This is just the overcount from when we added the probability of A and the probability of B. So we added the things that they share in common, the A and B. That's the stuff that occurs simultaneously. We've added that in A when we added A, and we also added that when we added B. So since they both had a common outcome, it was counted in both places. So it was counted double. So this subtracts off all that double, or that overcounting. That's a good example so we can make sense of this minus part. So we got a group of 25 baboons. 18 enjoy grooming their neighbors. 16 enjoy screeching wildly, right? And 10 enjoy doing both of these things. So we're going to randomly select one of these 25 baboons. What's the probability that it enjoys grooming its neighbors, or, right, again, keyword here, or, that means I know I can use that rule. Alright, or screeching wildly. So what I'm being asked to do here is find the probability. I'm going to put G for grooming. Oops. G for grooming, or S for screeching. Okay, so the rule says that I split that up and add each one individually. The probability it enjoys grooming plus the probability it enjoys screeching. Alright, and then we'll subtract off the probability it enjoys both grooming and screeching. Alright, that's what we're being asked to do. Now remember, these are probabilities, so these are going to be fractions. So when we set it up, there's 18 that enjoyed grooming out of the 25 total. There were 16 that enjoyed screeching out of the 25 total. And there are 10 that enjoyed both. So we end up with 18, 16, 10, and we end up subtracting the overcount. So 18 and 16 added 34. 34 over 25 doesn't make any sense as a probability. Right? Remember, they have to be less than 1. So we subtract off the common 10 that are common to both, and we take away the overcount. So there's 24 out of 25. So if you're familiar with Venn diagrams, you can create a Venn diagram if it helps you with these. So I got G for grooming, S for screeching, and there's a crossover here. In this crossover, that's where these 10 animals go. Alright, and now the grooming, it says that there's 18 total in this whole entire group. Well, 10 of them are already accounted for from the intersection, right, where the two circles cross. So that means that this number out here, to get me to 18, has to be 8. And now the entire G circle has 18 in it. Alright, and then likewise for screeching, I got 10 in the middle that enjoy both. So how many are right here? Well, it's got to be, to get to 16, it's got to be 10 plus 6. So 6 go here. Alright, now there's 25 total in the group. If we add it up, we got 8, 10, that's 18. 18 plus 6 is 24. To get to 25, that means we got 1 out here on the outside. This is the sample space. I guess I shouldn't have used S for screeching. I'm going to put SC and GR. So that can be S for the sample space. I have to have 1 out here to represent everything. So what does this 8 mean? It means they enjoy grooming, but they're outside the SC circle, so they don't enjoy screeching. So 8 like grooming one another, but they don't like screeching. Alright, the 10, that's obviously the ones that like both. There's 6 that enjoy screeching, but they don't like being groomed. And then there's 1 out here on the outside, and a little outsider that doesn't like grooming. He's not a part of this circle, and he doesn't like screeching. He's not a part of this circle. He doesn't like either. So he belongs to the group because he is one of these baboons, but he doesn't like doing either of these two things. Okay, so you can use Venn diagrams to help you with these things if you want to help visualize it with these probabilities, these OR probabilities. But you can also just use the OR rule. Now notice this 24, I could add these 3 numbers and get that 24 just as easily as I could have used the rule. That's what I'm wanting you to see, that this, from this information, 25, 18, 16, 10, enjoy doing both. I do the 10 first, alright, and then I complete the circle. So 10, so that means this has to be 8, 10, that means this has to be 6, 8, 10, and 6, that's 24, so that means this has to be 1. And now I could really answer any probability question you throw at me about these things. Alright, odds. Odds and probability are not the same thing. Alright, they're definitely kin, and they definitely are giving you a measure of likelihood. But one cannot be bigger than 1 ever, and the other one very much can be bigger than 1. So the odds in favor of an event E occurring is the probability the event does occur divided by the probability the event does not occur. Okay, and just so you know, you can also use n's here. Alright, n, if you go back and look at your earlier notes from the previous section, n means the number of ways, the number of outcomes. So you could also just count the number of outcomes that satisfy the event occurring and the number of outcomes that satisfy the event not occurring, and just do it that way. Make a ratio with just the numbers rather than the probabilities. The problem with using probabilities to find these odds is that you end up with decimal divided by decimal, or worse, fraction divided by fraction. And a lot of people just have trouble when fractions are involved, especially fractions within fractions, like this suggests. So I would suggest doing it with numbers if you can. And then the odds against, all we do is just take the reciprocal of the previous one. Notice this is on top, and then this is down below. Right? And likewise, we could do the number of things that don't satisfy the event divided by the number of things that do satisfy the event. So we could use numbers or probabilities. Alright, and then this is just mentioning that they are reciprocals of one another. So let's do one. I want to show you that we could get this via probabilities like the example suggests, and how it's going to show you, if you click on view an example, it's going to show you probability paths, not using numbers. But I'm going to show you that it does work with numbers. Alright, you roll a single 6-sided die, find the odds in favor. So the odds in favor are the probability that it happens divided by the probability it doesn't happen. So if we want to find the odds in favor of rolling a 2, we need to find the probability we do roll a 2, which is 1 out of 6, and divide that by the probability we don't roll a 2, which is 5 out of 6. Okay, so remember there's our 2, so there's one way I could get it. There's 1, 2, 3, 4, 5 ways that I don't get it. Okay, so 1 out of 6 divided by 5 out of 6, notice because we're dividing, we flip this bottom one. That's what's going on here, is we're dividing by this fraction. So how do you divide by a fraction? You flip it and multiply by it. So the 1/6 was being divided by 5/6. That's the same thing as 1/6 being multiplied by 6/5, the reciprocal of 5/6. We just flip that thing over, and that's how we divide by fractions. We multiply by the reciprocal. The 6's cancel, and we're left with 1 over 5. Alright, but if you look, this is the odds, so this is the number of things that satisfy the event, the 2, divided by the number of things that satisfy the complement of the event, or the event not happening, which is 1, 2, 3, 4, 5. So 1 over 5. So you can also just think of this as numbers, and that way you avoid the division of fractions. Alright, odds to probability. If you're given the odds A to B, now it's very important that you find that word 2 when you're doing these, and take that word 2 and look in front of it. That's the numerator. Add the 2 together. That's the denominator. Okay, but the 2 will be the one that separates numerator from the 2 things that you add together to get your denominator. Alright, let's practice one. The odds in favor of a particular horse winning a race are 2 to 5. What's the probability? So we take the 2 that's in front of the word 2, the number 2 that is, alright, and we put that in the numerator. So there's the 2, and then we add the 2 and the 5 together in the denominator. So 2 divided by 2 plus 5, and that gives us our odds, our probability. Alright, remember this will always be a proper fraction. Alright, at very worst, the numerator denominator will be equal, but you'll never have a probability where the numerator is bigger than the denominator. This is also true for the odds against. Okay, we just have to do something a little bit different. If the odds against are A to B, so same thing as before, but it's odds against now instead of odds in favor, you have to remember for odds against. Remember, for odds in favor, this was the number of things that satisfied the event, and this was the number of things that satisfied the event not happening, reduced. Okay. Well, if it's odds against, remember these are reversed. So this is the things that satisfy the event not happening, reduced, and then this is the thing that satisfies the event happening. So if we want to find the probability the event does happen, then it is the number of things it's always the number of things that satisfy the event on top, so B gets on top, and then the total number of possible outcomes. So the event happening and not happening will always add up to the total number of outcomes. So there's our probability. So this time, if you're given odds against to find probability the event happens, you use the thing that follows 2 for the numerator and then add up. So if it's odds in favor, then whatever's in front of 2 is your numerator, right? But if it's odds against, the thing that follows 2 is your numerator.